kind of a food for thought for you. With a stringed instrument, it's easy to tune the instrument because the frequencies that it's going to give you, NB/12, you can tune the instrument easy by fixing the velocity of the wave in a string. Well, how do you do it? Velocity of the wave in a string is the tension over the mass density of the string, right? We saw that equation in chapter 16. So by tightening the string with different tightnesses and using different string lengths and thicknesses, we can change the mass density of the string. So the faster, the tighter we make it, right? The higher the tension, the faster it will travel. And the thinner the string, the lighter the string, that will also cause it to travel fast. In other words, the strings that are gonna make the highest frequencies are the thin strings and the tightest strings, right? Thin, thinnest, and tightest. Those are high frequencies. So when you pluck a string, you predominantly will hear the fundamental frequency. The N is 1. But it will also make all the higher harmonics too. But those are harder to hear. But their amplitude is not as strong as the first one, right? So when you pluck it, what it's probably gonna do, see like this, it's gonna make this, but then it's also gonna make this wave. Then it's gonna make this wave. You know, all the overtones, like this, like that, hold on. It's gonna go like this, like this, like this, like this, right? Then the next one is what? Up, down, up, up, down, up. I'm not drawing it good. Up, down, up, up. God. Should be up, down, up. In other words, when you pluck the string, it's probably making all the harmonics, but they have less and less amplitude. You see what I'm trying to say? You could draw. This is the fundamental frequency. This is the first harmonic. Fundamental frequency, first harmonic. Second harmonic, first overtone, right? And then the next one is going to be, if this is up down, it should be able to go up down up. And meet it at there, right? So up, down, up, and then meet it at there. Then another, imagine this is the, I should go like this. This is the center. See that? Of course, when you pluck it, you don't see these. They're so minuscule, you know, that you don't see it, but that's happening there. The next one is going to be what? Up, down, up. But you see here how the amplitude of this is less than this, and the amplitude of this is less than that. So that's why you predominantly hear N is 1, right? So if you want to tune the string, it's very easy by tightening the string or lowering the tension, right? The thickest strings are going to give you, so if you had a thick string like this, they're going to give you, since this is thick, they're going to give you the less frequency. So a thick string gives less frequency. Is that true? Anyone play guitar or violin or cello? Thicker string gives you the less, right? Do you put them at the same tension? Are the tensions the same? Huh? That probably depends on the demand of that particular instrument, the cello or the violin. In other words, what's by standard, what should the violin, the thickest string, be giving you as its fundamental frequency, right? So that probably has to do with tradition and our musical notes or whatever. Maybe if you're playing some random modern music which doesn't follow the same patterns, the music might call for other frequencies, you know. But if you're playing the typical classical music that has certain regulations, okay, so the thick string should be giving you this frequency. The next one should be giving you this one, you see. So then the demand of that standard, you put them at a certain tension. So it's not necessarily that they're the same. Okay? But how about for a wind instrument, clarinet, flute, any of those, trombone, trumpet? So for that one, you just have closed, open. These one would be they're called the reed instruments. Reed instruments, such as clarinet, and I believe saxophone. So they're closed and open. The closed end is where you put your mouth where the reed is. Right? So in an actual instrument, it would look like this. You put a little piece of wood, and then when you go like this, close the reed, but you blow into it, but you also close it at the same time. And then the reed vibrates slightly, but it's actually the closed end. And then it's going like this, and then wherever you press the thing, the wave comes out of that end, right? Wherever, let's say you press it, when you're pressing it, it's actually opening the hole. You press it like this, something like this. So if you press it here, it's opening the hole, and the wave is leaving from there. You see? So this is where you're actually blowing into the closed end, because as you're blowing, you're closing the lid with your lips. I have a clarinet at home. I'm trying to learn, but it's too hard. So I'll bring it one day and I'll show it to you guys. Then you got the flute. Where there's an opening here on the side, and this is your mouth. Nose. Okay, that one you're not closing anything. You're just blowing into the open hole, right? You're blowing into the open hole, and then it goes, and then again, wherever you press, it escapes from there, right? So you have two open ends. So this would be wind instruments. Okay. Flute. What else?
Accordion.
Huh? Accordion?
Accordion.
Accordion? No, I don't think accordion you blow into it. That one? That's a pipe. Oh, that's our. There's a whole class of them. I don't know which one they would fall under. Accordion. I'm not sure. Flute. Can't think of any other. This one, I think, bassoon. I think bassoon is probably a reed instrument.
What about a trumpet?
Trumpet is brass instrument.
Oh,
The physics of that is pretty complex, but they say it more mimics wind. Trumpet, and of course trombone, right? So those are brass instruments. They say it's kind of those ones are complex because it's a combination of closed and open, so it's a very complicated thing going on with brass instruments. Okay, so with those, how can you manipulate the equation? F sub n is nv over 4L, right? And then this one is F sub n is nv over 2L. Okay? So, what can you do? Well, you blow into it, right? And then by you pressing the finger, you determine the length, right?
Right.
So you can make it very short length. So if you press the one that's close to you, right, then it's going to escape and the length is going to be short. So it shouldn't give you the highest pitch, the highest. And again, you're only going to hear you're going to determine the L, you're not going to determine the N. You determine the L, and the one that you hear is the N is 1 in that case, right? You hear N is 1 because N is 3 and 5 and 7 is going to have less amplitude. And the amplitude of this is even going to be less than the 2, right? Because here you hear 1, 2, 3. 2 has less amplitude than 1, but 3 always has less amplitude than 2, right? So you only hear 1, 3, 5, but of course you hear predominantly 1. So the only thing you can control is where you press the finger. How about the velocity? What determines that? Well, it's not this equation anymore, Q over mu. What determines the velocity of the wave in the instrument?
U.
What's the equation? It's the velocity of sound waves in the instrument, because these are not string waves that you're creating. You're blowing into it and you're creating a sound wave, which is a longitudinal wave, and the velocity of that wave is just simply a factor of the temperature in the air. Can you change that? Well, it depends whatever the temperature in the air is. So how do you tune your instruments then?
Every time walk into a new room.
I don't know if you can tune it. Anyone play one of those instruments? Depends on the temperature in the stage you're in. Or maybe it depends also on the temperature coming from your breath. Some combination of that temperature coming from your breath and the temperature in the room. And that one I don't think you can tune. The only thing you can do is just press. So then if you have an orchestra and the guy says, okay, now everybody tune it. And then you see the violin going zzz, and then everybody has to tune theirs to the violin. So what do the wind instruments do?
Sit there.
They should have a bucket of ice, right? Put the flute in the bucket of ice, because that's gonna cool the air inside of the flute, right? That's probably the only way you can tune it. So that's usually I see that. There's a bucket of ice next to them.
Oh,
No,
really?
there isn't. I'm
I was
joking.
like, what? I was like,
But that literally would be the only way to tune it. Just put it on some hot water or cold water. Hot, cold, and then you go like this, and then you put a thermometer in there. Okay, that's about right. Now let's blow it. But literally, that's the only way to do it, is change the temperature. How about if you take in some helium, and then you put helium in there. You blow helium in there. What's that going to do to the velocity? Well, no, it's no longer this equation. Its velocity of the helium is going to be square root of the bulk modulus of helium over the density of helium, right? Remember we saw in that chapter, the density of helium is much lower than air, right? Which is the velocity of helium is much higher than velocity of the sound in air. So what's that going to do? That's why when you inhale helium and you talk, it produces much higher frequency, right? So if you inhale helium into there, what's going to happen? The instrument is going to make much higher frequencies. And that'll be kind of fun. See what kind of music you get. Continually blow helium into it and then play into it, right? It's going to make a lot higher frequencies like that. Cool. Well, now I thought of another instrument, maybe flute and piccolo. Piccolo is that little tiny one, right? Do they make high frequencies or low frequencies?
Hi.
Huh?
High.
Very high, because they're small.
Yeah.
So they have small L. You see? Have you ever heard the sound that water makes? Let's say you get a graduated cylinder and you fill it up with water. What happens as the graduated cylinder fills up with water?
It starts to get higher.
That's another illustration of that, right? Because the water is dripping into the graduated cylinder and the water is filling up. you're hearing the bouncing of the sound as the water goes, hits the top surface of the water, and it's creating a sound that's coming back up to your ear, right? So what kind of a pipe is that? It's acting as it's acting like I think closed and open. Because the top of the graduated cylinder is open, right? And this bottom is closed. Goes down, bounces, comes back up more like a clarinet.
Oh, and the sound that trap, because at my house on the sink, I can also, I don't touching the water when it's really cold, so I turn on the hot, and I can hear the difference from when it's really cold to when it's hot, and then I can know when to place
When
everything.
it's hit off the surface of the sink?
No, it's like I hear it coming from.
Oh, coming?
Yeah.
Oh, it's making a different sound.
It makes
That
a
could be
different
it,
sound.
because the heat, the temperature is changing the velocity, yeah. Yeah, so as it's going up, you should hear a lower and lower pitch, right? As the graduated cylinder is going up. So all those things now, I want you to notice, you know, how instruments play, how do they tune their instruments. Okay, last maybe 15 minutes, let's now start the temperature chapter.